Okay, two things we're going to look at in this video are sampling distributions of a sample mean and then something called the central limit theorem. So in the previous videos, we talked about confidence intervals and how they relate to a proportion. Does it change at all for a sample mean? And the quick answer is no. It still takes on the same process of you get your sample mean, you add or subtract 2 times the standard deviation, but there's one little change, okay? And that change is whatever the standard deviation is, we divide it by the square root of the sample size, okay? So, for example, let's do a quick example actually while we're on this topic, okay? If I wanted to figure out the confidence interval, let's say my sample mean is 25, and we'll say it's 25 years old. We want to try and figure out the average age of the players in the NBA playoffs, okay? And I don't gather the entire population of players in the playoffs. I select a sample size of just 16. I'm going to use 16. It's a nice perfect square. And in that average, and I'm also going to use this symbol X bar, I get 25 years old. So this is what my 95% confidence interval would be. I would have, we always use this equation for sample means, X bar plus or minus 2, and then in just parentheses here, I'm going to put Z star, because remember, that can change, that 2. Okay, but for 95% confidence, we use the number 2. And then it's going to be the standard deviation all over the square root of n. That's where this thing changes the most. I have to remember to take my population standard deviation and divide it by the square root of n. So it's going to look like this. 25 plus or minus 2 times, now I haven't figured out the standard deviation just yet. We'll get to that in a minute. But then here's the key part down here is I'm going to divide by the square root of 16. Okay, because my sampling distribution of means will always have a standard deviation that is relative to the population standard deviation, just divided by the square root of my sample size. Okay, now let's make this thing even easier. Let's say my standard deviation is 4 years old. Okay, or 4 years, I should say. So the standard deviation is 4 years. So I can put that 4 into my equation. 25 plus or minus 2 times 4, the square root of 16 is 4. And let's finish this up. So we have 25 plus or minus 2. 4 divided by 4 is 1. So plus or minus 2. So my confidence interval is going to be between 23 years and 27 years old. So I'm 95% confident the true population parameter of average age of NBA playoff player. Kind of running out of room here. I apologize. Whoa, where'd that go? Let's get back to this. Of NBA, I'm 95% confident the true population parameter of average age of NBA playoff player is between 23 and 27. Okay. Now, that explains where that square root of sample size comes from. Let's go back to our PowerPoint for a second to explain one more concept before we show you some things on the Rossman Chance app. The central limit theorem. Central limit theorem is something that is a beauty, meaning we can take any distribution, whether it's skewed left, skewed right, and if we take averages from that distribution, and then we look at that distribution of the averages, it's going to attempt to take on a normal distribution. Okay, so for example, we looked at a corporation that has salaries that are basically skewed right, which we've gone over before, meaning that the bulk of my employees make a salary somewhere in the middle, and then I have a few outliers on the top end, upper management, that make a lot more money. They draw the average up. It's a skewed right distribution. If I randomly take samples of 10 employees, okay, and I take 50 different samples of 10 people. And in those samples, I could have people repeat, but each sample is significantly different. And in those 50 samples, I take the average salary. And then of those average salaries, I look at a distribution, I look at a histogram. It's going to look fairly normal. All right. Now, if this concept is difficult to understand, we're going to use our trusty old friend here, Rossman Chance, and we're going to go back to the home page, and there should be an option for sampling pennies. Okay, I love this exercise because it just makes a lot of sense. Okay, so over the tabs here, you're going to click on this option, pennies, and what we see here, let's look at the list first. Okay, it's a list compiled of 1,000 different pennies with the year and then their age as of 1999. So for example, in this first row here, we have a penny that is from the year 1995, and let's say current day is 1999. This is definitely outdated. It's 4 years old. Okay, now one would imagine that this would be a skewed left distribution because most of my pennies in circulation are going to be closer to a newer age, right? In other words, as we see here, if this is the year, this represents the year 2000, this represents the year 1980, this is 1960, this is 1940, I'm going to see most of my pennies that are in circulation towards this higher end here, right? That makes sense. But now, see what happens when I take averages, okay? So what we're going to do is we're going to take one sample of sample size 10, and I'm going to change this number to 16, and you're going to see why in a minute. So what I'm doing is I'm going to simulate taking 16 randomly selected pennies from this group of 1,000. Okay, now your numbers may be different. And here's that most recent sample. Okay, so the average year I got was 88.875, so basically 1988. Okay, my standard deviation is 7.64. But then over here, it's going to list this diagram over here is going to measure out all the different samples that we collect. And we're going to do a bunch of them. So here's the first one, and it's right here. Okay, my standard deviation is not applicable just yet. Just give it a minute, and it should work. Okay, let's draw 10 of those samples now. Okay, so here we go. We just added 10 more blocks. Now, it probably doesn't look normal, but it might look a little more normal than the population, right? The population is very skewed left. This one's just kind of like, we can't really tell for now. Let's draw 1,000 samples. This takes a while, but 1,000 samples of sample size 16, and let's see what kind of distribution we get. Now we're in business. Look at this. Look at how normal this looks, okay? Because we're taking, again, the averages. What this diagram over here represents is 1,000, technically 1,011 different samples of sample size 16, okay? I want you to notice a couple things. One, the shape of it is normal as compared to the parent function or the parent distribution that's skewed left. The second thing, I want you to take a look at the mean. The mean here is 86.675. The mean here is 86.7. So it's pretty darn close, okay? It's really not that far off between the two values, okay? But here's where I really want you to see this relationship between the standard deviation. Okay, my population standard deviation is 9.6. My standard deviation here is 2.375, okay? Where did that number come from, okay? We'll go back to our confidence interval, okay? How did we calculate standard deviation? We took the standard deviation and we divided it by the square root of n. So guess what? If I look at my population standard deviation of that distribution, I'm just going to divide this up here in a second, okay, which again was 9 and some change. Let's get that number exactly, 9.613, okay? And if I now take that and divide it by the square root of n, or I divide it by the square root of 16, let's just see what I get. So 9.613 divided by 4, and we can use our calculator to help us. So I'm going to do that. Again, it's going to be, let's flip back here, 9.613, 9.613 divided by 4, I get 2.40325. Does it look familiar? Okay. Take a mental note of that number and go back to our distribution here and check this out. our standard deviation over here is 2.375, 0.02 of a point off from this calculation, okay? That's why that rule exists. That's why we divide by the squared event, because we see it proven here. You're gathering data that's more consistent. Anytime we gather averages of any distribution, whether it's skewed left, skewed right, normal, always going to be more consistent.